Welcome to Data Science 1, Probability, Expectation Rules. What we're going to need to know is we're going to need to know what a probability density function is. We're going to need to know what expectation is. We're going to need to know what a marginal probability density function is and a conditional probability density function. Well, not really the last two, but we do need to know the other two. Okay, so if you remember back, a ways back, where we were talking about expectations for univariate, meaning one variable, we had defined for discrete, it was the expected value of x is the sum of x times f of x, and for continuous, the expected value of x was the integral from negative infinity to infinity of x times f of x dx. So we extended this into the general form when we just had some g of x as a function of x. So here for the discrete, we would just sum over all the x's, and for the continuous, we would just integrate over all of the x's. So same idea. Okay, so we easily want to be able to work with this g of x, okay, because we came up with the idea and we'd like to reduce the amount of work that we need for it. So there are three basic rules that go with this. Okay, so the expected value of c is equal to c, where c is a constant. The expected value of c times g of x is equal to c times the expected value of g of x, where c is a constant. And if I have two functions, g of x and h of x, and I add them together, then it becomes the expected value of g of x plus the expected value of h of x. And these are really, really easy to show. And some of this should make sense. So, for example, the expected value of a constant. What do I expect 5 to be tomorrow? 5 is a constant. Do I expect it to be anything different? No, because it's random, okay? And again, pulling this constant out seems to be reasonable. If I'm going to have 5 times whatever some random quantity is, well, I can expect it to be 5 times whatever the mean of that random quantity is. And the addition is easy as well. Okay, if you wanted me to justify this for you, rule number 1, the expected value of a constant is a constant. It's the same constant. Just use your properties of integrals. You can do this with properties of sums as well, and you get the same place. But notice you just factor that out because constants come out of integrals. And we know that this is a density now, and this integral is equal to 1. So bingo, no problem. Okay, so here, how do I know to pull this out? Well, it's expected value of c of g of x. Write it in integral format. We know that since it's a constant, it can come outside the integral. So, and then if I stare at this is just the expected value of g of x. Super easy. Okay, same deal here. Use the definition, plug it in. This time, distribute the f through. And then note that you can, integration goes across addition because it's really just a sum. So here we get this piece and we get this piece, and if I stare at them, this is the expected value of g of x, and this is the expected value of h of x. So pretty easy. All right, so basically this is what would be called the properties of a linear operator. It goes across addition, constants pull out, and constants stay the same. Super easy. All right, so here's our example that we're going to work through. So suppose I know the expected value of x is mu of x, and the expected value of y, I'm going to denote mu of y, and we want to find the expected value of this thing. Now, I could start off by taking this and shoving it into an integral, and then doing all the rules and whatever, but that just takes way too long. So here we go. So I've got a, here's my thing. I just stick it inside of my expectation operator. I immediately know that it goes across addition, right? That was one of my things that I know I can do. And I know I can pull constants out. And I know that the expected value of a constant is a constant. And then I just plug in what I know about these, right? I've already defined those. And this becomes my answer. It's pretty easy, and it's kind of what you would expect it to be. But later, things don't behave like you would think they will when we get to variances. All right, so remember back when we started with a variance, we defined sigma squared as the variance of x, and this is what it was defined to be. And we want to know, what can we learn from this? Well, if I start here and I just keep moving on, I can expand this out. So x squared minus 2x mu plus mu squared. Well, then I can use my properties that I have so far. So this is the expected value of x squared minus the expected value of 2 mu x plus the expected value of mu squared. Well, okay, so 2 mu is a constant, so it can get pulled out, and mu squared is a constant, so it can get pulled out. Then I get the expected value of x squared is 2 mu times mu, because the expected value of x is mu, plus mu squared. And this boils down to the expected value of x squared minus mu squared. And this is really a shortcut formula for later. So if you have to do lots of variances, you calculate the expected value of x, which is what mu is, and then you calculate the expected value of x squared, and you've got everything you need to know. But suppose we know sigma squared and mu squared, well, then we also know the expected value of x squared. This is just an identity that comes out of this that comes in handy every now and then. All right, so there are 3 basic rules. The expected value of a constant's a constant. Constants pull out, and that we can go across addition. So these will become really, 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 really important later. So I can't stress that enough. And I know this has all been theoretical. There's no numbers, and you're like, what are we doing? We're trying to get ourselves to a point where we can determine distributions of test statistics. That's ultimately where we're going with this. But first, we got to know what we're looking for. So this gives us some structure that we can work with later. And we'll move on to the next video, which is about variances. So see you there.